Dear students, welcome back to Electromagnetic Waves and Transmission Lines course. Today we will discuss Module 5, Transmission Line 2. Here we will discuss input impedance relations, reflection coefficient, VSWR, average power, shorted lines, open circuited lines, and matched lines, low loss radio frequency and ultra high frequency transmission lines, ultra high frequency lines as circuit elements, and finally Smith chart, construction and its applications, quarter wave transformer, single stub matching, and illustrated problems. First, we will discuss about what is phase velocity and group velocity. Phase velocity and group velocity. Um, First, propagation constant gamma is equal to alpha plus j beta, where alpha is the attenuation constant, beta is the phase constant. Uh, for wave propagation, the voltage wave equation V of z comma t is proportional to e power j omega t minus beta z. The phase velocity is defined as the speed at which a constant phase point travels along the line is called phase velocity. For constant phase, omega t minus beta z is equal to constant. That is, by differentiating that equation, omega dt minus beta dz is equal to 0. That is, dz by dt is equal to omega by beta. Here dz by dt is called the phase velocity. Vp is equal to omega by beta. For lossless transmission line, the phase velocity Vp is equal to 1 by square root of Lc. Since beta is equal to the phase constant is equal to omega square root of Lc, omega by beta is equal to phase velocity. Therefore, omega by beta is equal to Vp is equal to 1 by square root of Lc. For distortion-less transmission line, also the phase constant beta is equal to omega square root of Lc. Here also the phase velocity is equal to 1 by square root of Lc. Now, group velocity is defined as it is the speed at which the envelope of a modulated wave travels. The group velocity Vg is equal to d omega by d beta. For lossless transmission line, since beta is equal to omega square root of Lc, dB by d omega is equal to square root of Lc. Vg also equal to 1 by square root of Lc. For lossless transmission line, Vg is equal to Vp. For dispersive transmission line or general lossy transmission line, the phase velocity varies with the frequency. If beta is not proportional to omega, then the phase velocity is not equal to the group velocity. Then Vg is equal to dB by d omega whole power minus 1. For important observations here, for lossless transmission line, the phase velocity and the group velocity is same. For lossless and distortion transmission line, the phase velocity and group velocity are same. For lossy transmission lines or dispersive transmission lines, the frequency is dependent on the phase velocity. So the phase velocity and group velocity are different. Now, the transmission lines input impedance. Here, will see the transmission line of length z is equal to 0 to z is equal to L. Here Vg is the transmission line connected to the generator and ZL is the load impedance. Here ZIN is the input impedance. ZIN is equal to VIN by IIN. From general voltage and current equations from transmission line theory, Vs of Z is equal to the forward wave and the reverse wave. Similarly, the current wave equation equal to forward current wave and reverse current wave, and the propagation constant gamma is equal to alpha plus j beta, and the characteristic impedance Z0 is equal to square root of R plus j omega L by G plus j omega C. Now applying the boundary conditions at the load Z is equal to L, the voltage Vs of L is equal to VL, Is of L is equal to IL. From equation 1 and equation 2, you can write VL is equal to V0 plus e power minus gamma L plus V0 minus e power gamma L. From equation 2, IL is equal to V0 plus divided by Z0 e power minus gamma L minus V0 minus divided by Z0 e power gamma L. Multiplying equation 4 with Z0, you will get Z0 into IL is equal to V0 plus e power minus gamma L minus V0 minus e power gamma L. Now solving for V0 plus and V0 minus, by adding the equation 3 and equation 5, you will get V0 plus is equal to VL plus Z0 IL divided by 2 e power gamma L. Similarly, subtracting the equation 5 from equation 3, we will get V0 minus is equal to VL minus Z0 IL divided by 2 e power minus gamma L. Evaluating at the input Z is equal to 0, from equation 1, we will say that when Z is equal to 0, Vs of Z is equal to Vin, that is Vin is equal to V0 plus V power V0 minus, since Z is equal to 0. Similarly, the values of V0 plus and V0 minus will substitute here. By rearranging the terms, we will get Vin is equal to, this is the expression. Here, the hyperbolic function of cos hs is equal to, hx is equal to e power x plus e power minus x by 2. Similarly, sin hyperbolic x is equal to e power x minus e power minus x by 2. So by rearranging these terms, you can write Vn is equal to VL cos h gamma L plus Z0 IL sin h gamma L. From equation 2, also we'll get IIN is equal to, this is the equation. By substituting this V0 plus and V0 minus in this equation and simplifying that, we'll get IIN is equal to VIL divided by Z0 into sin hyperbolic gamma L plus IL cos hyperbolic gamma L. From input impedance, ZIN is equal to VIN divided by IIN. By substituting equation 8 and equation 9 in the above equation, we will get this expression, and factor IL using ZL is equal to VL by IL, ZIN is equal to ZL cos hyperbolic omega L plus Z0 sin hyperbolic gamma L. Similarly, here ZL by Z0 sin hyperbolic gamma L plus cos hyperbolic gamma L. Now, by multiplying the numerator and denominator by Z0, we will get ZIN is equal to Z0 ZL cos hyperbolic gamma L plus Z0 sin hyperbolic gamma L divided by Z0 cos hyperbolic gamma L plus ZL sin hyperbolic gamma L. The alternative compact form for the input impedance of the transmission line. Now, dividing the numerator and the denominator by cos hyperbolic gamma L, we will get the expression in terms of tan hyperbolic gamma L. That is ZIN is equal to Z0 ZL plus Z0 tan hyperbolic gamma L divided by Z0 plus ZL tan hyperbolic gamma L. For lossless transmission line case, the attenuation constant alpha is equal to 0. The propagation constant gamma is equal to alpha plus j beta. Alpha is equal to 0. Therefore, gamma is equal to j beta. We can write the input impedance for lossless transmission line ZIN is equal to Z0 ZL plus Z0 tan hyperbolic gamma L. Gamma is equal to j beta L. Then we can write this is equal to j tan beta L. Okay, this is a very simple expression. Similarly, for the denominator also Z0 plus JZL tan beta L. Okay, here we can see the hyperbolic and trigonometric identity tan H Jx is equal to J tan X. Okay, for the property of lossless transmission line, R is equal to 0, G is equal to 0, the propagation constant gamma is equal to J beta. Now the final result for the input impedance of transmission line Zin is equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Now the transmission line equivalent diagram for input impedance you can write here. This is a generator side, this is a load side, this is Zin. Here this is a VIN. VIN is equal to VG into Zin divided by Zin plus ZG. Similarly, IIN is equal to VG divided by Zin plus ZG. This is a generator impedance. The input impedance for different lengths of transmission lines, we'll see the transmission line length L is equal to lambda by 8 and transmission line length L is equal to 2n plus 1 to lambda by 4, and case 3 the transmission line length L is equal to n into lambda by 2 where n is equal to 1 to 3 and so on. For case 1 the transmission line length L is equal to lambda by 8, the general input impedance Zin is equal to by substituting L is equal to lambda by 8 in the input impedance equation, beta is equal to phase constant, beta is equal to 2 pi by lambda, where L is equal to lambda by 8. Therefore, beta into L is equal to pi by 4. By evaluating this tangent tan beta L, that is equal to tan of pi by 4, that is tan 45 degrees is equal to 1. Substituting it into this value in the input impedance formula, Zin is equal to Z0 into ZL plus JZ0 divided by Z0 plus JZL. Therefore, the magnitude of Zin, this is equal to Z0. Now, we have the case 2 where the length L is equal to 2n plus 1 to lambda by 4 for lossless transmission line. The general input impedance formula here is given here. Now, substitute beta into L. L is equal to, suppose when n is equal to 0, L is equal to lambda by 4. When n is equal to 1, L is equal to 3 lambda by 4. Now, substitute n is equal to 0 here. Beta into L is equal to 2n plus 1 to pi by 2, and tan of 2n plus 1 into pi by 2, tan pi by 2, that is equal to infinity. By substituting this value in the impedance equation, Zin is equal to Z0 JZ0 by JZL. Now Zin is equal to Z0 square divided by ZL. Okay, when length L is equal to lambda by 4, then the transmission line is called quarter wave transmission line. L is equal to lambda by 4, therefore beta into L is equal to 2 pi by lambda into lambda by 4. This is equal to pi by 2. Since tan pi by 2 is equal to tan 90, that is equal to infinity, the input impedance Zin is equal to Z0 square divided by ZL. Now coming to the case 3, the length L is equal to n into lambda by 2. When n is equal to 0, when n is equal to 1, this is lambda by 2. Now the beta into L is equal to 2 pi by lambda into lambda by 2. Therefore, beta into L is equal to n into pi. By evaluating this tangent tan n into pi for different values of n, this is equal to 0. By substituting this into the input impedance formula, Zin is equal to, this value is 0, therefore Z0 into ZL by Z0. Therefore, For length L is equal to n into lambda by 2, the input impedance is equal to the load impedance. For the transmission line length L is equal to n into lambda by 2, the input impedance is nothing but the load impedance. Similarly, the input impedance for different load conditions, we'll consider first one is Z is equal to 0 is called short circuited, and ZL is equal to infinity is called open circuited transmission line. First case, the short circuited transmission line ZL is equal to 0. The input impedance of a short circuited transmission line, short circuited means ZL is equal to 0. Therefore, ZIN is equal to, by substituting ZL is equal to 0 in the input impedance equation, ZIN is equal to Z0, J Z0 tan beta L divided by Z0. Input impedance when load is short circuited is denoted by ZIN is equal to ZZC. This is the short circuited transmission line input impedance. That is equal to JZ0 tan beta L. Similarly, the open circuited transmission line input impedance, that is denoted by ZOC, open circuited transmission line input impedance. This is equal to ZL is equal to infinity. By substituting this ZL is equal to infinity in the input impedance equation, ZIN is equal to Z0 1 by J tan beta L. Since 1 by tan x is equal to cot x, you can write the input impedance when the load is open circuited is denoted by ZIN is equal to ZOC. Therefore, ZOC is equal to minus J Z0 cot beta L. Now, the relationship between the open circuited and the short circuited input impedance is given by ZSC into ZOC is equal to Z0 square. Or you can write the Z0 is equal to square root of ZSC into ZOC. Z0 is the characteristic impedance. Dear students, in our next class we'll discuss about the reflection coefficient. Thank you. Welcome back, dear students. Today we'll discuss about the reflection coefficient. The reflection occurs in a transmission line at the load due to the mismatch at the load. Okay, let us consider a transmission line as shown in the figure. VIN is the input voltage, ZIN is the input impedance of the transmission line, Z0 is the characteristic impedance of the transmission lines, ZL is the load impedance, and Z is equal to L. The length of the transmission line is small l. Okay, VG is the at the source or the generator, and ZL is at the load. The coordinate system used at here is at the load Z is equal to L, at the input generator point Z is equal to 0. So the distance along the line is measured from the generator towards the load. The voltage and current wave equations is given below. Applying the boundary conditions at the load Z is equal to L, that is V of L is equal to VL, I of L is equal to IL, you can write this expression. Now, VL is equal to IL into Z0. This is equal to V0 plus e power minus gamma L minus V0 minus e power gamma L. By taking the Z0 outside, you will get this expression. Z0 into IL is equal to V0 plus e power minus gamma L minus V0 minus divided by Z0 e power gamma L. Now, by simplifying the equation 1 and equation 2, by adding the equation 1 and equation 2, we will get the expression V0 plus, and subtracting that also will get the value here. Now the reflection coefficient is defined as the voltage reflection coefficient is defined as this is rho v is equal to V reflected divided by V incident. This is the reflection coefficient, voltage reflection coefficient. At Z is equal to L, the incident wave and the reflected wave is given by these equations. Therefore, by substituting this, we will get V naught minus divided by V naught plus e power 2 gamma L. By substituting these two equations, we will get the voltage reflection coefficient is equal to ZL minus Z naught divided by ZL plus Z naught. Please solve these expressions. This is the final answer. Similarly, the current reflection coefficient also is defined as, this is the current reflection ratio, reflection coefficient, that is equal to I reflected divided by the I incident. This is the incident current and this is the reflected current, right? Therefore, the current reflection coefficient, by substituting V naught plus and V naught minus, the incident voltage, will get the expression. Now, the reflection coefficient at any distance Z from the load also we can able to find out in between the Z is equal to 0 and Z is equal to L also we can able to find out. This is the voltage wave equation on a transmission line. These are the reflection coefficient at any point. Z can be defined as VR of Z and VI of Z. VR of Z is the reflected voltage at Z, VI of Z is the incident voltage at the Z. Now, these are the expressions for the incident and reflected voltages. The reflection coefficient is equal to the reflected wave divided by the incident wave. We will get this. At the load Z is equal to L, we'll get the reflection coefficient is this V naught minus divided V naught plus e power 2 gamma L. Expressing the reflection coefficient in terms of the reflection coefficient at the load, we can write the reflection coefficient at any point on a transmission line Z is the expression of the reflection coefficient at the load into e power minus 2 gamma into L minus Z. For lossless transmission line, gamma is equal to J beta. Therefore, the reflection coefficient at any point on the transmission line is equal to the reflection coefficient at the load multiplied by e power minus 2 or J beta into L minus Z. Similarly, we can able to calculate the voltage standing wave ratio. The voltage standing wave ratio is defined as the voltage standing wave ratio is defined as V maximum divided by the V minimum. The ratio of maximum voltage to the minimum voltage is called the voltage standing wave ratio. The important cases of voltage standing wave ratio VSWR is for perfectly matched line, that is ZL is equal to Z naught, and the partially matched line ZL is not equal to Z naught. The open circuit load ZL is equal to infinity and short circuit load ZL is equal to 0. Okay, we will see each case. The important cases for the voltage standing wave ratio. Okay, this is the reflection coefficient. This is the voltage standing wave ratio. The relationship between the VSWR and the reflection coefficient is given by VSWR is equal to 1 plus magnitude of the reflection coefficient divided by 1 minus the magnitude of the reflection coefficient. For perfectly matched line, the condition is ZL is equal to Z0. Perfectly matched line, the VSWR is equal to 1. What is the physical meaning here? For perfectly matched line, there is no reflected wave, only the forward traveling wave exists. Voltage magnitude is constant along the line. For partially mismatched line, where ZL is not equal to Z0, the reflection coefficient value varies from 0 to 1. The VSWR value varies from 1 to infinity. The physical meaning for partial mismatch of the transmission line is some power is reflected back. Incident and reflected waves interfere. They forms a standing wave appears. Now coming to the open circuited load, ZL is equal to infinity. The reflection coefficient is equal to +1, and the VSWR is equal to infinity. For open circuited load, the entire wave is reflected. The reflected wave has same phase as the incident wave. The voltage maximum occurs at the load. Coming to the short circuited load, ZL is equal to 0. The reflection coefficient tau is equal to -1. VSWR also equal to infinity. What is the physical meaning of the short circuited load? The entire wave is reflected, but the reflected wave is 180 degrees out of phase with the incident wave. The voltage becomes 0 at the load. This is the summary for the VSWR and the reflection coefficient here. For perfectly matched lines, ZL is equal to Z0, the reflection coefficient is 0, VSWR is equal to 1. This is for partial mismatch, and some power is the reflected, and this is the ZL is equal to infinity is the open circuited line, and this ZL is equal to 0 is the short circuited line. The VSWR and the reflection coefficients are given here. Thank you, students.